Hello everyone, welcome back to Physics 425. In a previous video, what we were talking about were kind of practical systems that we could use to get to 1 Kelvin using a bath of pumped liquid helium-4 or 300 millikelvin using a bath of pumped liquid helium-3. And when we drew the possible experimental setups to do that, we also identified the various mechanisms by which heat could flow into our low temperature bath. And the mechanisms were conduction through like solid structures, conduction by a residual gas, and radiation. And so what we're going to do next is talk about each of those heat transfer mechanisms one at a time. And today we're going to start with radiation. So the first thing that we're going to do is recall the Stefan Boltzmann Law. And so this law talks about a surface at a temperature T, and this surface will radiate power determined by A, the area of that surface, epsilon, its emissivity, sigma is a constant, it's the Stefan Boltzmann constant, and it's temperature to the 4th power. So it's a pretty strong, actually, function of temperature. So A is the area of the surface. Epsilon is the emissivity. And we'll just make a note that for a so-called black body, the emissivity is equal to 1. So that's the maximum power radiated by a surface is when a surface is a black body. And then sigma is the Stefan Boltzmann constant, and it's given by 2 pi to the 5th kb to the 4th over 15 c squared h squared. And you've put in the numbers for all those constants. It's 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4th. Actually, this constant's not so difficult to remember because it's 5, 6, 7, 8. Anyways, this is the Stefan Boltzmann constant. Okay, what we're going to be interested in low temperature physics is what if we have 2 parallel surfaces, like the walls of a dewar or something like that, at different temperatures. What's the heat flow between those surfaces? And so we imagine that we have some wall or some surface, and so we'll call this the top surface. We'll call this surface 2, and then below that we have a bottom surface of some thickness, right? Maybe a glass wall of a dewar or something, and this is surface 1. And so we'll imagine that this first surface has a temperature T1. It has something we're going to call the absorbance alpha. So this is going to have alpha 1. And then over here we have surface 2 at temperature T2, and it has its own absorbance alpha 2. Okay, so we'll come back to this picture. We're going to add things to it. So we consider two parallel surfaces at different temperatures. Okay, and so in a time delta t, surface 1 emits energy. Okay, so power is energy per unit time, and so the amount of energy that's emitted in a time delta t is given by P delta t, where this power P is obtained from the Stefan Boltzmann Law. Okay, and so let's say the surface is radiating power P1 and the top surface is radiating power P2. Okay, so this emits energy E1 is equal to P1 delta T, and this is energy emitted in the form of photons. All right, so we go back to our picture here and we say, so we have energy E1 that's emitted from this bottom surface, and it's directed towards the second surface. Okay. So when this energy or this stream of photons hits the second surface, what will happen is surface 2 absorbs a fraction of the incident energy E1, and the amount of energy that it absorbs is equal to the absorbance E2 times the amount of incident energy E1. So alpha is the absorbance of a surface. Okay, so if it absorbs a certain fraction of the incident energy, it's going to reflect the remainder. Okay, so surface 2 also reflects a fraction of E1, and the reflected fraction is equal to, let's say, rho to E1. So rho is the reflectance of a surface. And so we'll just note that, as you'd expect, if we take the reflectance and we add the absorbance, that has to be equal to 1, or we could say that the reflectance is equal to 1 minus alpha. Okay, so if we go back to our picture then, what we can do is we can indicate that a certain amount of energy has been absorbed, and that absorbed energy is alpha 2E1. But then some of it's just reflected back, and the amount reflected back is E1 times the reflectance, which is 1 minus alpha 2. Okay, good. Okay, so then after that, what's going to happen is we're going to have an amount of energy equal to E1 times 1 minus alpha 2 incident back onto the first surface. So surface 1 will absorb. There's an incident energy E1, 1 minus alpha 2. And the fraction that is absorbed is determined by alpha 1, the absorbance of the first surface. And so surface 1 will also reflect. A part of that incident energy, and the amount that is reflected is 1 minus alpha 1 times the incident energy. Okay, and so we could go back to our picture and we can add that stuff in. So this incident energy comes in, some of it's going to be absorbed, and that's E1, 1 minus alpha 2, alpha 1. And the remainder is reflected. And so this reflected portion is E1, 1 minus alpha 2, 1 minus alpha 1. And you can see what's going to go on. This is, again, we're going to have energy back incident on surface 2. It's less energy now because we've lost some to absorption at the surfaces. But anyways, this goes on. So surface 2 is going to absorb. Okay, so there's going to be an incident energy E1, 1 minus alpha 2, 1 minus alpha 1, and then it's going to absorb a fraction of that. That fraction is determined by alpha 2. And surface 2 is going to reflect. So there's incident energy E1, 1 minus alpha 2, 1 minus alpha 1, and the reflected portion is 1 minus alpha 2. Okay, so we go back to our picture, add this stuff in. Incident on surface 2. Some of it's absorbed. How much is absorbed is E1, 1 minus alpha 2, 1 minus alpha 1, alpha 2. And then there's some reflected, and that's E1, 1 minus alpha 2, 1 minus alpha 1, 1 minus alpha 2. Okay. We'll do one more iteration of this, and we'll say that surface 1 is now going to absorb. So the incident energy is E1, 1 minus alpha 2, 1 minus alpha 1, 1 minus alpha 2, and the absorbed fraction is determined by alpha 1. Surface 1 reflects. Incident energy is E1, 1 minus alpha 2, 1 minus alpha 1, 1 minus alpha 2, and then the reflected part is 1 minus alpha 1. Let's add this to our picture. So this energy comes and it interacts with the first surface. Some energy is absorbed. It's E1, 1 minus alpha 2, 1 minus alpha 1, 1 minus alpha 2, and then alpha 1. And then there's a reflection. That's E1, 1 minus alpha 2, 1 minus alpha 1, 1 minus alpha 2 times 1 minus alpha 1. All right. And so I'm going to stop drawing these and writing down these terms, but this just keeps going on and on and on and on indefinitely. So far, what we've only considered is energy emitted by the bottom surface, surface 1, but we could likewise talk about the energy that's emitted by surface 2. And everything would be the same. We would just have to change all the subscripts. Instead of an energy emitted E1, we'd have an E2 energy emitted, and then we would have all of our terms of alpha 1s and alpha 2s. So we can do the same calculation for surface 2. So it would look like surface 2 emits an energy E2, surface 1 is going to absorb E2 alpha 1, surface 1 is going to reflect E2 1 minus alpha 1, and then of course we just keep going. Alright, so let's go back and let's focus in on the first part of the calculation where we imagine surface 1 emits an energy E1. So what we could do is we could say the total amount of the energy E1 that is absorbed by surface 1 is. Okay, now it's useful to go back to our picture here, and the amount of energy absorbed by surface 1 is this term added to this term added to all the other parts that we didn't write down. Okay, and so let's just start writing down all those contributions. So the first contribution is this. So E1 is the original amount of energy that was emitted. 1 minus alpha 2 was the fraction that was reflected off of surface 2, and then the alpha 1 is the amount that was absorbed at surface 1. And then we have our second term, which is included in our picture, and it looks something like this. If we drew the next term, it would be, so E1, and then the amount reflected from 2, the amount reflected from 1, the amount reflected from 2, the amount reflected from 1, the amount reflected from 2, and then the amount absorbed by 1. And so each time there is, before it gets back to surface 1, there would have to be a reflection off 1 and a reflection off 2. So every time we add a term, we have to add a 1 minus alpha and a 1 minus alpha 1 and a 1 minus alpha 2 factor. Okay, so when we look at all these terms, there's some common factors. E1 times 1 minus alpha 2, E1 times 1 minus alpha 2, E1 times 1 minus alpha 2, and then there's a common alpha 1 at the end. And so we can factor these things out, and we could say, well, when we add up all these terms, we could re-express it as E1, 1 minus alpha 2 times alpha 1. Those are all the common factors. And then we have a 1 plus 1 minus alpha 1, 1 minus alpha 2, plus, and then over here we have 1 minus alpha 1 and 1 minus alpha 1, so we get 1 minus alpha 1 squared. And then we have 1 minus alpha 2 and 1 minus alpha 2, so we get 1 minus alpha 2 squared, plus, and so on. Right, there would be a 1 minus alpha 1 cubed times 1 minus alpha 2 cubed, and then the fourth power and fifth power, and so on. So let's, for simplicity, or to reduce how much we have to write, let's define this combination as beta. And in that case, the amount of E1 absorbed by surface 1 is going to be equal to E1, 1 minus alpha 2, alpha 1. And then it's 1 plus beta plus beta squared plus beta cubed plus beta to the fourth, and so on. This is equivalently written as the sum from n equals 0 to infinity of beta to the n, which is a geometric series, and that geometric series has the following solution provided that beta is between 0 and 1. And it has to be, because if alpha 1 is the absorbance, then 1 minus alpha 1 is less than 1, right? We can't have an absorbance greater than 1. And same thing with 1 minus alpha 2. That's also a number that's greater than 0 and less than 1. And so we have a product of two numbers that are less than 1, and that means that what we have is a geometric series with beta between 0 and 1. And so that's the solution. Okay, so the amount of E1 absorbed by surface 1 is E1 1 minus alpha 2 alpha 1 divided by 1 minus beta. And so that's kind of a nice clean result, right? We went from an infinite number of interactions of these photons with the surfaces after reflection, after reflection, after reflection, and we get a nice compact result. Okay. So then we could also ask, what is the amount of energy E1 that's absorbed by surface 2? Well, I think we could go and we could make a similar type of argument. We could probably write down a geometric series and then write down the sum of that series, a geometric sum. But the other thing we could do is we could say, well, if we know how much was absorbed by surface 1, then whatever's left over must be what was absorbed by surface 2. So if we take the total energy E1, subtract it by what we know was absorbed by surface 1, then the remainder is what was absorbed by surface 2. And so that's going to be E1, if we put things over a common denominator, times 1 minus beta minus E1, 1 minus alpha 2, alpha 1, 1 minus beta. So we could I think we can do some simplifications here. In the numerator, let's put in what beta was. Beta was 1 minus alpha 1 times 1 minus alpha 2. And then we have minus E1, 1 minus alpha 2, alpha 1. And we'll just leave beta as beta in the denominator. Okay, so let's write out some of these terms. So it's E1 times 1 is 1. And then we have minus E1. 1 minus alpha 1. And then we have minus E1. 1 minus alpha 2, and then we have minus E1, 1 minus alpha 2, alpha 1. Okay. Shoot, sorry, that's not right. Let me fix this. I made a mistake. So let's just take our time. It's minus E1, 1 minus alpha 1, 1 minus alpha 2, minus E1, 1 minus alpha 2, alpha 1, divided by 1 minus beta. Okay, sorry about that, but I think we're back on track. I'm going to expand some of these terms a little bit more. So we have minus E1 times 1 minus alpha 2. So it's minus E1, 1 minus alpha 2. And then we have minus E1 times minus alpha 1. And so that's plus E1, 1 minus alpha 2, alpha 1, minus E1, 1 minus alpha 2, alpha 1, divided by 1 minus beta. Okay, and now the nice thing happens is that these last two terms are identical except for the sign out front, and so they cancel. And moreover, we have E1 minus E1 times 1, so we could cancel this and we could cancel this. And so then we get E1 alpha 2, 1 minus beta. Okay. All right, so now what we've done is we've determined the amount of E1 absorbed by surface 2, and up here we have the amount of E1 absorbed by surface 1. Okay, good. So likewise, the amount of E2 absorbed by surface 1 is, well, it's the same expression, we just changed the subscripts, right? E1 becomes E2 and alpha 2 becomes alpha 1. All right, so the net transfer of energy from surface 1 to 2 is, okay, so from surface 1, energy E1 times alpha 2 divided by 1 over beta is the amount of energy that is transferred from 1 to 2. So this is the amount of E1 absorbed by 2. And then we have E2 alpha 1 divided by 1 minus beta, and that's the amount of E2 absorbed by 1. Or another way of thinking of it is the amount of E2 that's lost to surface 1. So therefore, surface 2 gains an energy E1 alpha 2 1 minus beta from surface 1, and it loses an energy E2 alpha 1 divided by 1 minus beta from its original energy that it had. Okay, so Q1 to 2 is going to be equal to, this can be put over a common denominator because they're both 1 minus beta in the denominator. All right, and so to gain further insight, let's think of a specific case. So if we have two surfaces at the same temperature and equal area. So let's imagine two parallel surfaces, like capacitor plates or something. Both those surfaces are at the same temperature. In that case, we wouldn't expect any heat flow between the two surfaces at the same temperature. So if we have these conditions, then the net transfer of heat or of energy is expected or required to be 0. And so in that case, that would only be true if the numerator in equation star was equal to 0. Okay, but this condition requires that E1 over alpha 1 must be equal to E2 over alpha 2. Okay, so let's do something else. Let's say we take one of our surfaces and we make that surface a black body. So a black body is a surface that absorbs all incident energy. So if we make surface 2 a black body, then alpha 2 has to be 1. That is, a black body is a surface that absorbs all incident radiation. We also know that a black body has an emissivity of epsilon equals 1. So for a black body, at least, the emissivity and the absorbance are both equal to 1. So if that's true, then it must be that we must have that E1 over alpha 1 is just equal to E2, because we made alpha 2 equal to 1 by virtue of making the surface 2 a black body. So we know that from the Stefan Boltzmann Law, E1 is A epsilon 1 sigma T to the 4th delta T, and E2 is going to be A epsilon 2, but because we have a black body, epsilon 2 is equal to 1 sigma T to the 4th delta T. Let's just emphasize that epsilon 2 is equal to 1 for a black body. Okay, so what that means is therefore A epsilon 1 sigma T to the 4th delta T is E1 divided by alpha 1 is equal to E2, so that's A sigma T to the 4th delta T. And so there's tons of cancellation here. We said we were going to make the areas the same. Sigma is just a constant. Temperatures were the same. If we wait the same amount of time, delta T, then those cancel. And what we have then left over is that epsilon 1 over alpha 1 must be equal to 1, or the results that we're trying to get at here is that the emissivity and the absorbance are the same. This is actually called Kirchhoff's law. So it's not Kirchhoff's law like loop law and junction law for circuit analysis, but this is Kirchhoff's law for radiating surfaces. And so what it says is that the absorbance is equal to the emissivity. Okay, so having established that, then what I want to go 2 is I want to return to equation star. Okay, so let's return to star and assume that we have parallel surfaces of equal area. But now we're not going to make the temperatures equal. They're going to be at different temperatures, and we can calculate the transfer of heat from one surface, from the hot surface to the cold surface. And so surface 1 is going to have an absorbance alpha 1, which we now know is equal to the emissivity epsilon 1, and same for surface 2. E1 for surface 1 is going to be A epsilon 1 sigma T to the 1, T1 to the 4th delta T. And surface 2 now it's not necessarily a black body, right? We just use that condition to establish Kirchhoff's law, but now surface 2 doesn't need to be a black body. It could have some emissivity different than 1. And it's at some temperature T2. Okay, so if we go back to star, then the heat transferred from 1 to 2 is going to be equal to A epsilon 1 sigma T to the 1 to the 4th delta T. That's E1. And then we multiply by the emissivity E2. So it was alpha 2 before. We're going to change that to epsilon 2. And then we subtract A epsilon 2 sigma T2 to the 4th delta T. So that's E2 times, it was alpha 1, but alpha is equal to the emissivity, so we'll put epsilon 1. And then we have 1 minus beta. And beta we can write as 1 minus epsilon 1 times 1 minus epsilon 2. Okay, so let's see, we have some common factors here. Both terms have an A, epsilon 1 and epsilon 2, a sigma and a delta T, and so the only difference is the T1 to the 4th and T2 to the 4th, and so this is going to be A delta T sigma epsilon 1, epsilon 2, T1 to the 4th minus T2 to the 4th. And in the denominator, we could multiply some things out. Let's see, we're going to have a 1, and then we'll have a minus 1 times 1 is 1. Minus 1 times epsilon 2 is plus epsilon 2. Minus epsilon 1 times 1 is plus epsilon 1. And then we have minus epsilon 1 times minus epsilon 2 is plus epsilon 1, epsilon 2, but there's a minus sign up front, like so. And so we can cancel the 1 and the minus 1. Okay, let's divide by epsilon 1, epsilon 2, and so Q from 1 to 2, the heat transfer from surface 1 to surface 2 is going to be equal to A delta T sigma T1 to the 4th minus T2 to the 4th. Then we divide by epsilon 1, epsilon 2. And so in the denominator, we're going to get 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Or the heat flux from 1 to 2 is, for heat flux, we'll use little q dot from 1 to 2. So it's the heat transferred from 1 to 2, which we just calculated above. And a flux is an energy per unit area per unit time. And so this is going to be sigma T1 to the fourth minus T2 to the fourth. It should be a fourth. Divided by 1 over epsilon 1 plus 1 over epsilon 2 minus 1. We could check a couple things to see if this makes sense. This is the flux from 1 to 2. So if 1 is at a higher temperature, T1 is larger than T2, then we get a positive heat flux. If, on the other hand, T2 is the hotter surface, then we get a negative heat flux. And so a negative flux from 1 to 2 means that we actually have heat transfer from 2 to 1. And so that makes sense. Hot surface transfers heat to the cool surface. Let's just finish with an example, a short example. What we're going to do is, in our experimental setups to get to, well, let's say just to 1 Kelvin, we had a pumped bath of liquid helium. And the way we did that is we had 2 dewars. And one dewar contained liquid helium, and the other dewar contained liquid nitrogen. And so let's imagine we have our 2 dewars. Inside this inner dewar is liquid helium-4, and so that the walls of that surface are at 1.2 Kelvin. And then out here, we have liquid nitrogen. And so this wall is at 77 Kelvin. And so we want to know what is the heat flux from the 77 Kelvin wall to the 1.2 Kelvin wall. All right, so Q dot from 1 to 2 is equal to sigma T to the 1 to the fourth minus T to the 2 to the fourth over 1 over epsilon 1 plus 1 over epsilon 2 minus 1. Okay, so first thing to note, and this is common, first note that 77 Kelvin to the power 4 is much, much greater than 1.2 Kelvin to the power of 4. So if you have a hot surface in low temperature physics, a relatively hot surface radiating heat to a very cold surface, usually the cold surface T to the fourth of that is negligible compared to the warm temperature. So T to the 1 to the fourth minus T to the 2 to the fourth, for all practical purposes, is just dependent on the T to the 1. And so we'll say that this is the T1 and this is the T2. So we can neglect the T2 to the fourth. The other thing we're going to need to do is to know what the emissivity of the two surfaces are. And for this flux, we want this heat flux to be as small as possible. To make that small, we want our denominator to be big. The way we make our denominator big is by making epsilon 1 and epsilon 2 as small as possible. Because then we have 1 over epsilon 1, which is large, and 1 over epsilon 2, which is large, and we could have a large denominator. So to make the heat flux small, we want epsilon 1 and epsilon 2 to be small. And so the way you make the emissivity small is by making the absorbance small, right? Because Kirchhoff's law said that emissivity and absorbance were equal. So if you make your surfaces highly reflective, then the absorbance is very small. And so you want shiny surfaces. So to make epsilon small, the Dewar walls are silvered. So that means they have a thin metallic coating that's very shiny and reflective. And this makes epsilon about, it might be 0.03 or something like that, 3% absorbing. So if epsilon 1 is approximately epsilon 2 is equal to 0.03, then our heat flux is going to be sigma, and we said we could neglect the T2 to the fourth, so we just have T1 to the fourth divided by 2 over epsilon minus 1, because 1 over epsilon 1 plus 1 over epsilon 2 is 2 over epsilon. And so that's sigma T1 to the fourth, and then it's 2 minus epsilon over epsilon, which is epsilon sigma T to the 1 to the fourth. And then 2 minus epsilon is 2 minus 0.03. So that's just practically 2. And this is equal to about 30 millijoules per meter squared second, or 30 milliwatts per meter squared. Okay, so if the Dewar is 1.5 meters tall and 12 centimeters in diameter, then you could multiply this by the surface area. A is going to be about 5.4 times 10 to the minus 3 meters squared, or the power transfer from 1 to 2 is Q dot from 1 to 2 times the surface area. And that's about 16 milliwatts, or 0.16 milliwatts, or 160 microwatts. Okay, and so what you could do is you could repeat this calculation. If you took the emissivity to not be small, not a nice shiny surface, but a dull surface where even take the emissivity as 0.5 and see how much this power load changes, and to see how important it is to have shiny surfaces to suppress the radiative heat transfer. All right.